Hello, dear students. Welcome to the channel and welcome to the Power System 2 class, in which we are discussing the power system and about the power system from very base. Uh, Up until now, we have seen a lot about power factor, we have seen about power system, we have seen impedance diagram, we have seen reactance diagram, we have seen how do we draw a single line diagram. We learned about per unit systems. So in the previous class we have seen how do we measure the per unit impedance, or how do we draw a per unit impedance diagram for the power system. With that, initially we have drawn what do you call it, a single line diagram of power system, and we have also drawn the reactance diagram of power system as well. So now we are going to talk about the power factor, and how do we control the power factor in the power system. But before going to that, we have to discuss about the synchronous motor, because one of the power factor compensation technique includes that, and it is very imperative to learn about the power system control. So so before going to the power system control, let's talk about the synchronous motor, or in general, synchronous machine. Okay. So if you remember, if you know the basics about synchronous motor, or even if you recall the basics about DC motor, there is a back EMF concept in it, right? If you remember, there is a back EMF concept. And what happens, the back EMF, which is called EB generally, it always acts in the opposite direction of the supply voltage. Basically, it acts in the opposite direction uh, of its origin voltage. So supply voltage is origin voltage, so it acts up in the opposite direction. Okay. And why is it generated? It is generated because the uh, generator action that takes place in your motor, you can say, right? So similarly, what happens with synchronous motor, with synchronous motor, back EMF is also produced in the stator conductors. So in this diagram on the left, you can see these are my stator conductors that you can see, small circles. These are stator conductors. This whole ring is my stator, and here inside we are having a rotor with north and south poles, magnets with it, right? So let's take a synchronous motor. Okay. So that's back EMF will be produced in the stator conductors, means in these, right? And when we connect this motor to supply, what will happen? Rotor will start rotating, right? What is direction it has shown? It is shown this direction, means the rotor will start rotating like this, means clockwise. Rotor will start rotating clockwise. Then uh, even though rotor is rotating, stator conductors will remain stationary, right? Stator conductors will remain stationary. And what will happen? These conductors will cut the rotating flux of the rotor. And if you remember the Faraday's law, because of how this conductor are cutting the flux, rotating flux, the EMF will be produced. Okay. And the EMF which has produced, or it's better to say induced, the induced EMF will oppose the cause of its production. Okay. It will oppose the cause of its production, which is the supply voltage in our case, right? So it will oppose the supply voltage. And by the way, if you're wondering where the EMF will be induced, so this EMF will be induced in the stator conductors, see here. Okay. So what will happen? This back EMF EB will act in the opposite direction of my supply voltage. So if my supply voltage is going in this direction, see here in this phasor diagram, if my supply voltage is going in this direction, then EB will be in the opposite direction, 180-degree phase shifted. It will be completely opposite direction. Okay. And Here you can see that we are having a supply voltage, three-phase supply, and this is my rotor. It will be something like this, and this will be my EB. Okay, so you can see that the EB will oppose my voltage, but there is one more thing, something a detail, little detail that you should notice, because it will be very useful in the future. That this phasor diagram is for no load conditions only. Okay, for no load conditions only, voltage and EMF are 180-degree apart from each other. Okay, now let's go to the equivalent circuit. But before going to that, let me show you the waveforms. This is the waveform of voltage. See, and as EB is 180 degrees shifted, that means it will be totally opposite. The waveform of EB will be totally opposite. Okay, ignore the magnitude for a moment, right? But uh, it will be in opposite direction. Okay, we will come to magnitude slowly. Now first let's discuss the equivalent circuit of synchronous motor. So look at this figure. On the left we are having armature circuit, on the right we are having field circuit. Okay, and we are providing three-phase AC supply to stator winding. So the armature reactance will be RA. Okay, and synchronous reactance will be XS. Okay, and where will this where will the EMF will be induced? The EMF, back EMF, will be induced in the stator winding. Okay, because uh, because of the because of cutting of flux, right? You can say because of excitation also, you can say, right? So this back EMF is also called, what is it called? Excitation EMF, because it is generated because of excitation, right? So it is also called excitation EMF, or given as EB here. See, and this is my field winding circuit. This is my field winding. Okay, um, the field winding resistance is RF, as you can see, and it is connected to my DC supply. Always remember, we are connecting field winding with DC supply, and it carries the field current of excitation. You can call it IF, like this, IF. Okay, now let's talk about the detail that I was talking about, that when what happens when we run my synchronous motor on load condition and off load condition. Okay, so when we put some load on my motor, what will happen? The speed of my motor will decrease, but it will decrease for only small moment of time. Okay, so it will be decreasing momentarily, and after a little time period, it will again start running at synchronous speed. Okay, it will again start running at synchronous speed, and it will continuously, since then it will continuously run on synchronous speed only. Okay, so now look at this figure on the left side. It is for no load condition. So what is happening here? See, the pole axis of stator and rotor are, see, co-inclined. See, both of them are co-inclined here, and rotor will be rotating at synchronous speed because we are not connecting any load with it. Now come to the right hand side image. What will happen when there will be a load connected to my synchronous motor? Okay, so first thing you must notice is that, see, these two are no longer in coincide, right? Pole axis and stator are pole axis of stator and rotor are not in coincide. Okay, then what is happening? The rotor is falling back. See, my rotor is falling slightly back, and the angle of which my rotor will be falling back will be called load angle, and uh, it is represented with delta. Okay, my load angle will be represented by delta. So what is in load angle? So it is the angle by which my rotor is falling back to my stator. Okay, so that is called load angle. Okay, now what will be the voltage, resultant voltage? Firstly let's talk about no load condition. What will the resultant voltage at no load conditions? So as there is no load connected, so resultant voltage will be uh, supply voltage minus uh, my EMF, right? V minus EB. So as there is no load connected, that means supply voltage will be equal to my EMF. So the resultant voltage will be zero, right? And as there is no voltage produced, there will be no current. There will be no current flowing in the circuit, right? Simple, pretty simple. Now let's come to the condition when my motor is loaded. Okay, so when motor is loaded, this angle delta comes into the picture. Okay, you can call it load angle, or you can also call it lag angle as well. Sometimes some people call it lag angle because rotor is lagging compared to stator, so it is also called lag angle. Here we will be calling it load angle. Okay, so what will happen, that the waveform of my voltage will will be leading, but the waveform of my back EMF will be lagging my supply voltage. Okay, let's come to this figure. Here you can see the waveform is now shifted with an angle delta here. See, this is left one is no load condition, right one is loaded condition. So see, when there is no load condition, then EB is equals to V, but it is 180-degree shifted, which means both of them will cancel out each other. See, voltage is going here, and EMF is going here, induced EMF is going here. So both are equal in magnitude and opposite in direction, so they will cut out each other. And at no load condition, there is no load angle, right? Because both my rotor and stator conductors are coincide. So sorry, rotor and stator pole axis will be coincide, so the load angle will be zero. But as we apply some load to my synchronous motor, the rotor will start to fall back. And because of this fallback of my rotor compared to stator, there will be a load angle. And because of this load angle, what will happen, my voltage will lead the induced EMF. See, voltage is starting from here, but EMF is starting from here, right? Because of this load angle, because rotor is falling back. So now let's try to plot it. Let's try to plot this angle. Let's try to plot it using phasor diagram. So here you can see we are taking V as a reference. See, V as a reference we took. And what is happening, EB is falling back at angle delta, right? EB is falling back at angle delta. So here we had 180-degree shift. Now there is some delta, some delta has been introduced, so it will still fall back. See, it will still oppose V, right? Still opposing V, so the direction will be negative, but there is delta. Okay, there is some angle, so it will be like this. Now if I want to draw the resultant of V and EB, what do I have to do? So what I will do, I will take this EB over here to the tip of the voltage phasor. So I will take my tail of EB at tip of the voltage supply voltage phasor, and then I will do the resultant vector. The resultant vector will be called ER. Okay, the resultant vector, we will call it ER. Okay, so let's come back again. When EB was in let's come back to no load. I mean, so in no load, what was happening, EB was in anti-phase with V. But uh, in case of loaded condition, what is happening? My EB is getting shifted by some phase angle delta. Okay, and this ER, which is resultant of V and EB, will so can you tell me what will be the change in ER if my load angle will increase? Okay, this is my delta. Okay, which is my load angle. So what will happen if load angle increases? I means it will go like that. So when it will go like that, what will happen? This will also come here, and also ER will also come here, right? So if the load on the motor is increased, the load load angle will also increase. Okay, load angle delta will increase, and when delta will increase, there will be change in ER, right? Now let's come to the current which is drawn from supply to be shown in the phasor diagram. Let's come to that. So the resultant voltage which is available across my stator winding, the resultant voltage, right? What is resultant voltage? My ER. So ER will be available across my stator winding, and let's shift the slide. It will be better when we shift it. See, this is ER, and it is available across my phasor winding. See here. So the winding is highly inductive. Always remember, the winding of synchronous motor is almost every single time is highly inductive. So the resistive component will be very small. It will be too small that you can even neglect the resistive component. Okay. So the current, because of this inductive element, what will happen? The current I will lag my resultant voltage, right? Current I will lag my resultant voltage because of this inductive effect. How much it will lag? Because there is the inductive effect is too strong, and resistance is almost negligible. That means it will lag by angle around 90. Okay, around 90 degree, because it is a case similar to pure inductive effect, right? So let's try to plot it. We will plot it with the we will denote that 90-degree shift in current with theta. Okay, and we will call this theta internal angle. We call this theta internal angle. Okay, and it can be found from impedance only. Okay, because R is negligible, so we can take theta is almost equal to 90, and then we can find it. Okay, so now let's try to draw the phasor diagram again. See, initially what we are doing, we are taking voltage here, voltage as reference, right? Then what did we do last time? Remember, there was some load angle delta, and because of that, EB was coming like that. It was not anti-phased with voltage, but it was still opposing voltage. So there is some EB. What will we do? We will again take this tail of the EB towards the head of the voltage phasor. Then we will draw the resultant. This resultant will be called ER. We've seen up till here. Now what did we just discuss? That my current will be lagging to ER at 90 degree. So see, this angle, if you will measure this angle between ER and I, this angle theta will be 90 degrees. Okay, and these angle phi, the angle between my supply voltage and my current, will be called phi, and the cosine of that angle is nothing but my power factor. Okay, the cosine of that angle is nothing but my power factor. So let's again quickly see all these angles that are playing part here. So see, first one was load angle, or we called it lag angle. It is represented by delta, right? And it depends on load, right? If load increases, then my delta also increases. Then the secondly, what did we had? We had theta. We called it internal angle. It is angle between my resultant voltage and current, and it is constant for any load condition, right? For any load condition, this angle theta will not change, right? Why it will not change? Because in any condition your inductance is not changing, right? The inductance of your motor is constant, so this angle will also remain constant. Then we had phi. We called it power factor angle. And what is it? It is angle between my supply voltage and current, right? Now there is one important thing which we can understand with the help of phasor diagram. uh, it is called V curves of synchronous motor. So we will go to that. But before that, before we go to that, let's say, let's derive the equation for I and ER. Uh, Initially I, and from that ER. So what is the equation of I? It is nothing but voltage divided by impedance, right? So uh, this I is induced in, we are getting the value of I because of this resultant voltage, right? So we will say ER divided by whatever the impedance will be there of my synchronous motor. So we will represent that impedance with the help of ZS. So current will be nothing but the ratio of ER divided by ZS. ER is my resultant voltage and ZS is my synchronous reactance, or you can say synchronous impedance. Because I'm saying synchronous reactance because we are neglecting the voltage. We are neglecting the resistance here, right? Uh, Also, you can say ER. What is ER? ER is nothing but the uh, arithmetic algebraic sum of V and EB vectors, right? We are taking V plus EB here. So it is nothing but vector addition of V and EB. So as EB is in the opposite direction, so we are taking V minus EB. Okay. And again from this formula, if I want to make ER subject, what will be ER? ER will be nothing but I into ZS. Okay, ER will be nothing but I into ZS, right? Now let's come to the next part. So now think that what will happen if we increase the load even further. Okay, see the previous case scenario, the load angle was up to that. What will happen if I increase the load angle further? Okay, so when we increase the load, what will happen? The load angle will also increase, right? And the resultant voltage IR will also increase, right? Because in previous case, see, load angle was that, and IB was here. Now when IB load angle will be more, IB will be something like here, and because of that IR will also be something like here, right? Which can be seen here. See, so the load angle will increase. With the increase of load angle, the resultant vector ER will also increase. And as ER will increase, this ER will increase, what will happen? The current drawn by the motor, right? Because what was the formula of current? See, I is equals to ER by ZS. So ER will increase, so current will also increase, right? Because Z is your constant. So my current will also increase. So as the load is more, with the more load, what happens? The with the increased load, you will need more current. So in short, if you want to conclude that, you can say with the higher load you will need higher current, right? And what do we do with that current? We send that current to uh, we what do we do with that current, right? Because if the current will be more, then need you will need better conductors, you will need better insulators, the cost will be more, right? So it is not very much very good thing, right? And uh, let's come to this figure. Here what we have done again, uh, we are having supply voltage, then as I've said, there is a load angle is increased, so there is more load angle is high, and because of that EB is the direction of EB will be like that. Again, let's take the component of EB here, and then draw a resultant. So the ER will be something here, ER will be more, ER will be high, and because ER is high, my current will also be high because I is 90-degree phase shifted, 90-degree apart from ER, right? So the delta is more, then ER is more, and ER is more, the current I is also more, right, for higher load. So now you have seen what happens when the load is higher. Now let's come to power factor and power factor control of my synchronous motor. So I hope up till now that a few things are very clear to you, that my back EMF is produced because of my rotor field, right? And this rotor field, or you can say excitation, you can adjust it to any value you find suitable, right? You can adjust your excitation with any desired value you find suitable. So the if the excitation will be more, then back EMF will be more, and if excitation will be less, then back EMF will also be less, right? So let's try to see it with the help of these phasor diagrams. See, the phasor diagram above here, it is showing for less excitation. Okay, so here we are having V. Okay, here is my V, and here we are having less excitation. Okay, less excitation means my load angle is less excitation means there is a less amount of load connected, which means my load angle will be less, which means uh, EB will be somewhere here, right? It will be close to anti-phasing with V. Now again, let's try to draw resultant. Let's take the tail of EB towards the head of V, and draw a resultant vector ER. So ER will be small here, right? And then at 90-degree or at theta angle, we will draw current component I. Okay, so I will also be here, right, lie here. Now let's try to draw it for higher excitation, right? So as the excitation will be more, the load will be more, load angle will be more, and because of this higher load angle, the EB will be more. I mean, EB will lie here, far from antiphase with supply voltage, right? And because of this, what will happen? We will take EB here again, and we will plot the ER resultant vector, and based on that, what we will do? We will uh, draw the current component at 90-degree from ER, right? So here see, in the when we are having less excitation, the angle between supply voltage and current is too much, phi 1 is too much. But when we are having more excitation, the angle between voltage and current is less comparatively, right? So when the load angle is constant, means load is constant, then theta, or you can say internal angle, will also remain constant, means it will also remain 90-degree, right? So we have seen that if this angle will in less excitation mode, the the phi 1 will be more, and in more excitation or high excitation, phi 1 will be less, right? So we can say that from this, that power factor we are having different, right? It is changing from phi 1 to phi 2, right? Or in other words, can't we say that my power factor is actually improving, right? Why am I saying that? See, what is power factor? Power factor is cosine angle between my voltage and current, right? So it is basically cos into phi, cos phi, sorry, not cos into phi, it is cos phi. Okay. So if my angle will be higher, let's say phi 1 is a very high value, is having so much higher value. So if my phi 1 will be high, which means cos phi will be high. And if you remember um, the table of cosine, what will happen as my angle increases, as the angle increases, what happens, the value of cosine moves towards zero. And as it moves towards zero, that your power factor will be less. And the power factor will be less, then your output power will be less, and your efficiency of your motor will also be less. Okay, which is bad, which is considered very bad for your motor, whatever motor you are using. Okay, we are having synchronous motor here. And in case of in this case, we are having phi 2 will be very less. So let's say it is very less, it is close to zero. So if my phi 2 will be, if my phi will be close to zero, so cosine of my phi will be what is the cos 0, it will be close to 1. So as it will be close to 1, so your power will be what is the equation of power, vi into cos phi, right? So as cosine's value is close to 1, the power will be very high. You will be able to utilize maximum amount of power you can get. So power will be high. So if the power will be high, that means uh, again your motor's efficiency will also be very high, and the performance of your motor will also be very good, right? Now if we increase the excitation even further, okay, so what will happen if we increase the excitation even further? The eb will also increase further, right? But in this case, what will happen? See, we initially we increased the eb this much, right? Where was I? Here. Again we increased eb, how much? This much. See, I came very close to V. Now what will happen if we increase EB that much, that I will uh, see in both of these figure, where is I is below the voltage vector, right? But what if we increase EB that much, that my I will surpass my voltage vector, and it will be placed over the voltage vector, right? So when such thing happens, we call that scenario, or we call the situation leading power factor scenario, or leading power factor situation, right? So uh, uh, this is how the power factor of motor can be controlled by controlling your excitation, or you can say controlling your field current, right? So let's keep this lecture till here. In the next lecture we will be discussing about the uh, synchronous generators power factor control. Today we have discussed about the power factor control of my synchronous motor. In the next lecture we will be discussing about the generator. If you are having any doubts, any queries, please feel free to mention down in the comments below. I will try to answer them as quick as I can. And I'll be meeting you in the next lecture. Till then, bye bye, take care everyone.